All right, now we're going to talk about how to generate the equations for calculating fraction folded for monomer trimer equilibria. And again, you're going to see that we've got the same sort of energy diagram representing two-state folding. That is, we proceed from the monomeric unfolded state through a single transition state down to the trimeric association state. And we have three monomers in equilibrium to form a trimer. Doesn't look much like a trimer. That's supposed to look like some kind of helix bundle. Maybe I'll try again. Okay, so as before, the difference in free energy between the three unfolded monomers and the folded trimer is going to determine our equilibrium constant. And our equilibrium constant we're going to define in terms of delta G. But because we know that this equilibrium involves three monomers in equilibrium with a trimer, we can also define the equilibrium constant as the concentration of the trimer divided by the cube of the concentration of the monomer. So at any given time in solution, if we let P equal the total peptide concentration, we've got trimer present in solution and we have monomer present in solution. But within each trimer are three monomers, so we have to take the trimer concentration and multiply it by 3 plus the monomer concentration, and that gives us the total amount of peptide monomer that we put in at the beginning of the experiment. All right, now because of the expression for equilibrium constant, we can rearrange and make some substitutions in our total peptide concentration expression. So for example, trimer concentration equals K times the monomer concentration cubed. Or in other words, and we can swap that, substitute that expression into the concentration of trimer in our total peptide equation. And if we subtract the total peptide concentration from each side, we're going to have this interesting cubic equation. It's a polynomial, and these are difficult to solve analytically. There are rules for certain kinds of polynomials, but this is one I can't do by hand. But sophisticated software programs can do them by hand. And so we're going to use Mathematica to find the roots of this polynomial. That is, what are the roots of this polynomial? They are values of monomer concentration such that this expression equals 0. Why do we want to know monomer concentration? Because ultimately, when we calculate the fraction of the total peptide that is folded, we're going to need that monomer concentration. Okay. And remember that once we calculate fraction folded, we then have something we can relate to our variable temperature CD observations. So now I'm going to switch to my computer so that you can see how we solve for the roots of this polynomial in Mathematica. All right, so we're in Mathematica now. I'm going to show you how to find the roots of that polynomial we just talked about for the monomer trimer equilibrium. This is actually really easy. I'm clear. The first line in my Mathematica code is usually clear all with brackets, and within the brackets you've got this global thing. I don't know why it has to be that way. I just learned it by Googling around, but this clears out all the variable definitions so Mathematica doesn't get confused. Alternatively, you can save variable definitions from earlier, but that's neither here nor there. So recall that our polynomial was, for the monomer-trimer equilibrium, 0 equals 3 times equilibrium constant times monomer concentration cubed plus the monomer concentration minus total peptide concentration. So that's our polynomial. To find the roots, I just need to type roots and put the polynomial in brackets, and then I need to tell it that I want to find values of m for which this expression equals 0. And with that there present, I just press shift and return. It wants me to make it an equation. So I need to put the equals 0. There we go. A little bit of syntax trouble. So here's the polynomial, and I had to put a double equal 0. I'm not totally sure what the double equal represents, but that somehow separates it from, that somehow defines that I want the equation to equal 0 instead of that I'm saying that all those variables equal 0. I'm not sure, and again, I found that out by Googling it. Okay, but you can see very quickly, and we can, now that we've got things figured out, we can show you how fast Mathematica is at doing that. Less than a second, and we have the 3 roots of this polynomial. And if you, in fact, plugged any of these numbers in for m, there are 3 here. By the way, they're separated by these double bars, and then you've got m equals this expression, m equals this expression, and m equals that expression. It's a cubic polynomial, so by definition there have to be 3 roots, though they don't all have to be real. They can be complex. And so for this polynomial, fortunately, we have 1 root, which is real, but I would have been able to come up with that on my own. And yet Mathematica is able to do that. And monomer concentration is defined only in terms of equilibrium constant and total peptide concentration. Total peptide concentration we know. Equilibrium constant we're going to fit based on an expression for a temperature-dependent expression for delta G. These other 2 roots, you'll notice, have I in them. I is the imaginary number. It's the square root of -1. These roots are complex. If you put them into this expression, the overall value will be 0, but they're not useful to us because they're imaginary instead of real. So we're going to take this expression for monomer concentration and plug that in to our fraction folded equation, and that's going to give us fraction folded as a function of equilibrium constant and total peptide concentration.